everyone, thank you so much for clicking onto this video. Today we're going to be looking at variable oxidation states. So we're going to look at how transition elements can show variable oxidation states using vanadium as one of the key examples. And then we're also going to explain about redox potential and also the reduction of Tollen's reagent to metallic silver, which is used to distinguish between aldehydes and ketones. Lastly, we're going to look at the redox titrations of iron 2+ and ethane dioate with manganate ions. And by the end, we should be able to perform calculations for these titrations and similar redox reactions. And now we're going to talk about variable oxidation states. So a key characteristic of transition elements is that they show variable oxidation states. And the redox potential for a transition metal ion changing from a higher to a lower oxidation state is influenced by pH and also by the ligand. In general, it is easier to oxidize a transition metal in alkaline conditions and reduce a transition metal in acidic conditions. So the first example we're going to look at is vanadium. So vanadium species can be found in oxidation states 4, 3, and 2, and they're formed by the reduction of vanadate 5 ions by zinc in acidic solution. And so first we have VO2+, which has an oxidation state of +5, and this is a yellow solution. Then we have VO2+, which has an oxidation state, well, the vanadium has an oxidation state of +4, and that's a blue solution. And V3+ is a green solution, and the vanadium has an oxidation state of +3. And for V2+, the oxidation state for vanadium is +2, and it's a violet solution. So you need to remember all of the colours of these solutions of these different species of vanadium. You don't really need to remember the oxidation states because you can just work them out. So, for example, for VO2+, you know that oxygen is -2. So then you have another -2 because we've got 2 of them. And so you get x minus 4 equals +1. So x must be equal to +5. So that's how they've got the oxidation state of the vanadium to be +5 there. And then the second example we're going to look at is Tollen's reagent and the reduction of Tollen's reagent. So this complex of silver and ammonias to make metallic silver is used to distinguish between aldehydes and ketones. So we'll be looking more on this in the organic topic, but just quickly now, what happens is that an electron is added to the Tollen's reagent, and so metallic silver is formed and also ammonia. And what is oxidized is the aldehyde. So here we have an aldehyde, which is just something with the group COH. So it's an organic molecule. And this is oxidized into a carboxylic acid, which is this. So aldehydes can be oxidized by Tollen's reagent, whereas ketones can't be oxidized by Tollen's reagent, and so they won't form the metallic silver. So that's how we distinguish between aldehydes and ketones. Now we're going to talk about manganate redox titration. Acidified potassium manganate is usually used to oxidize ethane dioate ions and Fe2+ ions. And so firstly, we're going to look at the redox titration of Fe2+ ions with acidified manganate ions. And so on the left, we have purple manganate ions. And the 8H+, these come from the acid. And so the manganate ions are reduced because we're adding these 5 electrons to form Mn2+ ions, which are colourless, and water. So reduction occurs. So we have reduction of manganate ions. And then the other thing that occurs is that Fe2+ is oxidized to form Fe3+ because it's lost an electron. And so we have the oxidation of iron 2+ ions. And so overall, if we combine these two half equations, we get that a manganate reacts with 5 of these Fe2+ ions and 8H+ to form Fe3+ ions, Mn2+ ions, and 4 waters. So in a normal titration, the purple potassium manganate is placed in the burette and the sample in the conical flask with dilute sulfuric acid. And this titration is actually self-indicating because of the significant colour change from reactant to product. The end product of the titration will be when the solution turns pink from colourless, as the manganate ions no longer react, so their colour remains. So basically the manganate ions are in excess. They start to become in excess. So that's when we see the first hint of pink colour. So an acid is needed to provide the 8 H+ ions. However, we need to choose a suitable acid. We actually use dilute sulfuric acid, and we also need this in the right volume, as insufficient volumes of sulfuric acid will mean the solution is not acidic enough, and so the MnO2 will be produced instead of Mn2+. And this MnO2 is brown, so it'll mask the colour change and lead to a greater volume of manganate being used in the titration. Here are some examples of unsuitable acids. So the first one is hydrochloric acid, and this is unsuitable because the manganate ions would oxidize the chloride ions to chlorine. So the chloride ions come from the HCl, and these would be oxidized to chlorine. So it would lead to a larger amount of the potassium manganate required, and also the chlorine produced is poisonous. Second, we have concentrated sulfuric acid or nitric acid, and these are unsuitable because they're oxidizing agents themselves. So they would lead to a smaller amount of potassium manganate required because they would also oxidize Fe2+. And the last example of an unsuitable acid is ethanoic acid. And basically it's a weak acid because it's an organic acid. And so it's too weak, so it doesn't provide enough H+ ions because we need 8 H+ ions. So it's really important to remember the examples of unsuitable acids, because in questions you'll be asked why we don't use, for example, concentrated sulfuric acid for this particular titration. And the last point is that if the ion is not in the +2 oxidation state, then we need to turn it into a +2. So if it is the element Fe, which has an oxidation number of 0 because it's just the element, then it's reacted with sulfuric acid to oxidize it to Fe2+, and then we can use it in the titration. And if it is Fe3+, then it is reacted with zinc to reduce it to Fe2+, because we can add an electron to it to form Fe2+, and then we can titrate it. But we need to remember to remove the remaining zinc after all the Fe3+ has reduced into Fe2+, because we need to stop the Fe3+ formed in the reaction being reduced back to the Fe2+ at the end. So the other redox titration with manganate ions that you need to know is with these ethane dioate ions. And so what happens is, again, the manganate ions are reduced themselves to form Mn2+. And so this is where reduction occurs. We have reduction of the manganate ions. And the ethane dioate ions are oxidized because they lose electrons to form carbon dioxide. So we have the oxidation of the ethane dioate. And so again, the manganate is acting as an oxidizing agent. And so overall, manganate and ethane dioate react in a 2:5 ratio. So we have 2 moles of manganate reacting with 5 moles of ethane dioate in an acidic solution to form carbon dioxide, the Mn2+, and also some water. Now, a really important thing to know is that MnO4- ions and ethane dioate ions are both negative, and so they repel each other. And this is why we need to warm up the reaction at the start of the titration, as otherwise the reaction will be very, very slow because they won't want to react with each other. And therefore, it takes a while at the start for the purple manganate 7 to react and be decolorized when it forms the Mn2+. And this is a really common exam question for this topic. So make sure you know why the reaction is rather slow at the beginning, because the 2 ions are both negative, so repel each other. However, the Mn2+ ions produced in the reaction act as catalysts, and so the reaction speeds up. So what we get is that the Mn2+ ions, which are formed from the overall reaction between the ethane diet and the manganate. They then react with the manganate to form this Mn3+. And then the Mn3+ react with the ethane diet to form more Mn2+. And so we have an endless cycle of the Mn2+ ions being produced and reacting and acting as a catalyst, which speeds up the reaction. And so this is what we call autocatalysis. And this is where one of the products acts as a catalyst for that reaction.